Before we start with memory management in the operating system, we first need a clear idea of what a memory address actually is. So let's take a very simple example. Imagine your computer has just 32 bytes of memory. Think of memory like a row of boxes, where each box stores 1 byte. So if we have 32 bytes of memory, that simply means we have 32 boxes. And each of these boxes has its own unique address, starting from 0 all the way up to 31. Now the question is, how many bits do we actually need to represent 32 different addresses? Since 32 is equal to 2 power 5, we need 5 bits to uniquely represent each address. In other words, every memory address here is just a 5-bit number. So what do these addresses actually look like? They're nothing but binary numbers. We start from all zeros and then count upward one by one until we eventually reach all ones. So in other words, we're just counting from 0 to 31, but representing each number in 5-bit binary. Now let's take this one step further. Instead of treating memory as individual bytes, we divide it into blocks. Let's say each block has 4 bytes. So now we have a total memory of 32 bytes, and each block is 4 bytes, which means we end up with 8 blocks. Now comes the most important idea. Each address is made up of 5 bits, and we split those 5 bits into 2 parts: the block number and the offset inside the block. Let's first understand the offset. Inside each block, we have 4 bytes, so we need 2 bits to select a specific byte within the block, because 2 power 2 equals 4. Now instead of looking at the entire memory, let's focus on just one block. Inside a single block, the addresses are consecutive, meaning they go from one location to the next in order. But here's the key idea. The block remains the same, while only the offset within that block changes, and that change is controlled by just the last 2 bits. Those last 2 bits cycle through 4 values: 0, 1, 2, and 3, which means they can select all 4 bytes inside the block. So here's the key idea. The last 2 bits tell us the exact position inside the block. That's what we call the offset. Since the total address is 5 bits and 2 bits are used for the offset, the remaining 3 bits naturally represent the block number. So every address is structured like this. First the block number, and then the offset. In total, that's 3 bits for the block and 2 bits for the offset. Let's take an example. Suppose the address is 10110. We split it into 2 parts. The first 3 bits, 101, and the last 2 bits, 10. Now, 101 corresponds to block 5, and 10 gives us the offset, which is position 2 inside the block. Now here's the key intuition. Within a block, memory is continuous, and in binary numbers, the rightmost bits change first. That means those bits change the fastest, which is why we use them as the offset. So every memory address is actually doing 2 things at once. It finds the block, and it finds the exact byte inside that block. This simple idea shows up everywhere, from cache memory to paging, and even file systems. So the next time you see a memory address, don't just think of it as a number. In the next video, we'll take this idea one step further. You've probably heard of terms like 32-bit and 64-bit systems. But what do they actually mean? Is it about speed, memory, or something else entirely? Now that you understand memory addresses, we're finally ready to decode this. And once you see it, it's surprisingly simple. So make sure you subscribe, and I'll see you in the next one.